Yeah, it's working. So welcome everybody to the morning session. And this morning we have the pleasure to assist to a talk by Iosif Bena from Université Paris-Saclay on the structure of the horizon.
Thanks. Thank you so much for the invitation to come here. It's my first time here. It's an amazing place. So this is work which has been going on over the past many years, but more recently, those are the people. Those are the people whom I have been collaborating with. Bogdan is also on the list, but I forgot him to. I forgot to put him. The guys in blue, and they are looking for faculty jobs. Those guys are looking for postdocs. They'll be in the market next year. So note the names and be careful when you make the offers. This is, again, the title is Structure the Horizon, What to Expect. I mean, everybody knows that black holes are causing a big problem between GR and quantum mechanics. Essentially, if you look at the biggest, fattest black hole in the known universe, this TON 618 quasar, the Bekenstein-Hawking entropy of this black hole is 10 to the power 98. So quantum mechanics says it has 10 to the power 98 states. That's e to the 10 to the 98 states. That's a lot of states. On the other hand, general relativity says it only has one state because there are no Hare theorems, which basically prohibit having any information on the horizon, and therefore this causes a problem. And this is the biggest unexplained number in physics. If anybody asks you, between this fat black hole, I mean between e to the 10 to the 98 and 1, this is the biggest number we don't understand in physics right now, all of physics. I don't think any other field of physics has comparable numbers. And the question is, okay. That's 10 to the 120. Yes, but this is e to the power 10 to the 90. So we are talking about e to the exponent of that. So we are at the exponent of the cosmological constant. So we are really way above that. I mean, cosmological constant is like nickels and dimes. If you solve this, that's. So the solution to this puzzle, okay, there are all these arguments about information and so on, but at the end of the day, the solution to the puzzle is that there should exist something at the scale of the horizon, some structure of the scale of the horizon. This was shown best by Matur, and also there are some arguments by Almeiri, Malov, Polchinski, and Sully from a bit later. There's another, and essentially what we are saying is that the black hole horizon, where this, where this stuff, there should be something. There should be some sort of microstructure. There's an alternative to this, which is very in vogue these years, which is called ER equals EPR, or islands. The problem with, at least for me, is that it involves wormholes and non-localities at some distances which are like megaparsecs, because essentially the non-locality has to be over the m cube, where m is the mass of the black hole. That's a non-locality which is too much to swallow. I'm a string theorist, I can swallow so many things, but megaparsec non-localities and transport of information at space like distances, megaparsec long, is something which I'm not willing to swallow. So for now, we'll play conservative. This is the conservative version. This is the crazy version. So just to set the point, transporting information over a megaparsec in no time, that's crazy. This, it's reasonable. But those are the only two alternatives. There's no other way. There's no other way to solve the information paradox. So the problem is, okay, structure the horizon, okay, very nice and beautiful, but how does it look like? Is it, what is the horizon replaced with? Is it some sort of geometry, or some sort of crazy solution, or some sort of thing? I just came up with the number. Take the biggest black hole in the universe, calculate m in Planck units to the power 3, express it in Planck units, it will come to be megaparsecs. It could be like, I mean, depends on the black hole. So for the T of I think it's, I don't know, I don't want to add the numbers, but it's really distances over the m cube, which should make everybody just, should make your hair go up. One should not accept such things, without a lot of evidence. So again, this is the, yes. Sorry?
Yeah, I'm very stressed out. Yeah, so if one is willing to accept these non-localities at very big scales, are there any other issues with this proposal that you wish? Issues is or
For me, this is the biggest one. Okay, there are some others, and Samir Matur and his ex-student Binguo, who is now a postdoc in Saclay, they have a big review article about problems. There are some other issues with ER equals EPR, but for me, the biggest one is the fact that information is supposed to be transported non-locally from one place to another space-like separation at a distance which is of order, which is macroscopic of order n cube. So that's something I'm not willing to accept. I'm a string theorist. Maybe I can accept distance of order m in Planck units. That's the black hole horizon. Maybe I can accept some non-localities. Even there's a problem, but okay. With a lot of effort, maybe I can explain some non-localities of order the mass of the black hole. But m cube, sorry. There's no way in any system of physics, string theory, anywhere where any such non-locality exists. But essentially they have this non-locality because they want to save the horizon. And if you want to save the horizon and preserve quantum information, you must have this non-locality or you must destroy the horizon. Those are the two options. And fuzzballs essentially are saying, look, you have to destroy the horizon. There's no hasta la vista. You have to replace it by something. Those guys say, no, the horizon is holy. We want to keep the horizon because it's in the Bible. And therefore, the horizon is holy and, we should live with the consequences. And the consequences are, those, non-localities and big wormholes. And okay, it's up to people to choose. But, for me at least, and, people who are not in the field, this is the crazy option. This is the down-to-earth, nice, conservative option. So the question is, okay, great. There's something at the horizon. How does it look like? Is it, non-violent, non-locality? How does it come? And people, this goes under the name, it's called echoes, extreme compact objects. And the point is, there are many, many proposals, gravastar, quark star, boson stars, modified gravity, mirrors, kept on floating by some pixie dust, Bose-Einstein condensate on gravitons, many, everybody and their brother, there's a huge amount of proposals of how to put something at the horizon. But the problem is that, okay, there are many proposals, but it's not so easy to do that. And when fuzzballs first appeared, Henry Horowitz basically told me, look, there's a big problem. All these things have been around for years. Ever since Hawking came with the paradox, everybody and their brother has been saying, let's put something at the horizon. Problem number one, if you replace the horizon by something, your structure should have black hole size for all the masses, or otherwise it should grow with G Newton the way the horizon grows. As you well know, if you make G Newton stronger, the horizon grows. If gravity is stronger, the Earth grows smaller, everything else becomes smaller. So whatever structure you put at the horizon, it should grow with G Newton the same as a black hole. And it's very complicated. Normal objects, again, they shrink, the black hole horizon grows, and the microstate geometries, which we will discuss, they have the same size as the black hole for all the masses. And this comes from a very deep string theory reason. They are made of solitons, which are non-perturbative degrees of freedom. Mass goes like 1 over G string, and therefore they become lighter when gravity becomes stronger. You cannot just put some replacement of the horizon. You need to use this kind of degrees of freedom. So this is lesson number one. If you want to build something to replace the black hole at all masses, you cannot just say, let's take some field theory with some things. You have to use non-perturbative degrees of freedom. You have to use solitons. This is lesson number one. So again, people use boson stars. In boson stars, for example, you need a scalar field of a different mass to replace a black hole. So you need the one scalar field for a solar mass black hole, another one for a 30 solar mass black hole, and so on. You just have to put more and more scalar fields for every black hole you want to replace. Here, what's happening is that you have the string theory non-perturbative degrees of freedom, which provide essentially for you this kind of dynamics. They provide essentially some sort of effective fields whose mass decreases for larger black hole, which can replace the black hole on a large size. So this is, one of the things which is nice. And again, boson stars are nice, and I think it's important to study them. But I think people should have in mind that there are toy models for some dynamics in some range at most. They should not be taken too seriously. Problem number two. Okay, great. Problem number one, the growth, and that's where it's important. Again, this is the first lesson. Problem number two, you have to have a mechanism not to fall into the black hole. This is some slice of a Penrose diagram, and we're trying to put something at the horizon. This is the horizon, the outer horizon. We're trying to put some garbage here. Okay, garbage here, nice and beautiful, but there's a GR dogma. You should not put anything at the horizon. Why is that? Well, very simple reason. The horizon is a null surface. If you want to put something there, it's a null surface, and therefore it should go with the speed of light. If it's massive, you do an infinite boost, infinite mass, infinite energy, bye-bye the solution. So, we're just garbage. If it's a massless field, you can solve the wave equation, and this is shown, and Harvey Real has some nice papers about this. If it's massless, it dilutes with time, so in a horizon crossing time, it will be gone. Essentially, anything you put here just wants to go up. It doesn't want to stay null. You just cannot put there spin, membranes, and quantum stuff. It just doesn't work. You need to put something there which stays there with some support mechanism. So lesson number two, if you don't have a support mechanism, again, you just cannot say I'm putting something there. You must have a support mechanism. Otherwise, time to go home and find one. And this is something called the quantum coyote principle. This is the coyote, which is running after the bird. And at some point, essentially the coyote is, realizing gravity starts acting, and the guy just falls down. And this is what's happening if you just put some mirror or some black box or something. Essentially the poor coyote just goes, oh, okay, sorry, what happened to this? Yeah, it just realizes gravity starts acting and starts falling. And that's what's happening in the horizon. It's a null surface. You just fall. You don't stay there. You have to look at gravity. Now this is problem number 2. Problem number 3, it's even worse. Problem number 3, essentially imagine some shell of dust collapsing again. Shown by Oppenheimer and Schneider back in Annus Domini 1939, that you put a shell of dust, you compute the collapse, and you find that the shell of dust forms the horizon. And again, imagine some super mega big shell of dust, which has the same mass as the TON 618 black hole. So the shell of dust collapses, and at some point the horizon forms. The horizon forms when at some point when the density of this thing is very small. I mean, the curvature of this solution is smaller than on the Earth. And the dust shell, of course, keeps on collapsing. The curvature is smaller than on the Earth. Why the heck should any quantum effects be important? So the horizon forms. This is the horizon, and this is the shell which keeps on collapsing. And the shell keeps on collapsing for another 180 hours. So that's a few days. And then at some point, the shell just goes and says, okay, hey, great, now I have a huge energy, I'm quantum, I have a singularity, all the quantum gravity effects start affecting me, and so on and so forth. And the shell, so I have, again, these red quantum gravity effects here, which are like, crazy and strongly coupled, horrible, horrible mess happening. But the horizon has already formed 180 hours ago. So, at this point, I have a horizon. What people are trying to do, they're trying to say, good, I have a structure at the horizon, I have a firewall, I have something happening. But to get these quantum effects and the strongly coupled region to form this structure at the horizon, it has to go back in time. And it has to go back in time, not for like 1 millisecond or some Planck time or something. It has to go back in time for 180 hours. That's a lot of time. That's a lot of time. And again, I'm not willing to accept such sort of violations of GR. I mean, again, I'm a conservative string theorist. Like, I'm not willing to accept megaparsec violations of locality. I'm not willing to accept, stuff going back in time for 180 hours. Sorry, that's just me. Maybe I'm too old. Maybe I should be more open-minded. But at this point, I'm not willing to accept such things. So the question is, how do you do that? How do you convince the shell of dust here, whose curvature is like smaller than on the Earth, to tunnel by to do something to form this firewall, to form this wall? How do you convince the horizon to be destroyed at this location? Because I want the horizon to be destroyed here. I don't care what's happening here 180 hours in the future. I don't care. I want the horizon to be formed here, and I don't want to go back in time 180 hours. And the answer is, to do that, there's an answer. There's a reason why quantum effects become important, and that has to do with the microstates of the black hole. If you look at the black hole, it has e to the s microstates, which again, we're trying to build. The probability of tunneling, of the shell of dust tunneling into one of them, is very, very small. I mean, I can tunnel into chocolate, for example. It's a very small probability. It can happen, but it doesn't happen. I don't go into chocolate. But it's a very, very tiny probability, e to the minus s. But because the black hole has so many microstates, it has a huge amount of microstates, the tunneling probability to go into them is over the 1. By Krauss and Matur using some generic arguments, but then Daniel and Andrea Pum and Bert and I showed, when Daniel was in the good old times as a grad student, we showed that actually for some system of brains collapsing into some bubbling geometries, you can compute this thing. You can compute this thing and you get on the nose e to the minus s with some coefficient in front, which is actually even a bit bigger than 1. So, we're talking about numbers, string theory calculations. I mean, those are not like some hand-waving guys and so on. This is really some tunneling calculation in a bubbling geometry, multi-center solutions with a full exact formula, and you get a number of this order with actually reasonably big constant in front. So it will tunnel. This tunneling will happen. So if anybody asks you, why does it tunnel in chocolate? I could go into chocolate right now. I could just undergo quantum tunneling. The reason is not that the tunneling probability is too small. That's one reason. But it's also that the entropy of chocolate is very small. If entropy, I could actually tunnel into chocolate because, the probability of tunneling is actually e to the minus s times how many n states I have available. This is the Fermi-Golden rule. So if I'm near a black hole background, I have a huge amount of states in that region, and the tunneling will be happening. Chocolate doesn't have so many states, so I don't tunnel into chocolate. But it's not because the tunneling probability is small. That's not enough. It's also the entropy of the final endpoint should be small. So this is the third phenomenon. It's an important piece of physics. And the point is, you need to have e to the s horizon-sized microstates. If you just have a black hole replaced, this is the third lesson, black hole entropy, the structure must have. if you only have something which has entropy 1, or like, one solution, or like, one solution of Einstein's equation, or 2, or 3, or 10, or like, 20, or, e to the 20, that's not enough. That's not enough. You need e to the 10, you need e to the 10 to the, sorry? Oh. This is not me, actually. This is GGI. It's okay. Signed up. It's okay. No, it's okay. No,
because that's Skype.
No. There's a Zoom entering, and Zoom just signs you out, but it doesn't mean that you still have all the privileges of sharing stuff.
Sorry, Iosif, one question. So you were mentioning that in this model there is a prefactor in front of e to the minus s, which is bigger than unity. Does that mean that the probability is bigger than unity?
No, because the timing, so the question is, when you approach the horizon, you can start, there's a timing probability. When you're like, twice the horizon size, then, you can tunnel with some probability. The more you approach the horizon, the bigger the probability is. So what this is saying is that, you're not tunneling straight at the horizon, you're tunneling a tiny bit before. But, okay, those are extreme black holes, so the horizon is some infinite depth. So, this is not, we don't have the exact, but the number in front, actually, if you look at what it means, practically, it means that you don't tunnel at the horizon scale, but you tunnel at the horizon scale plus some extra thing. But because you're doing extreme black holes, I cannot evaluate how much that extra thing is. I cannot tell you that it's, L Planck or like L Planck times square root of n or something. I mean, I don't think we did the calculation. So, it will happen, but, not really at the horizon, but, a tiny bit before. But again, we didn't evaluate the tiny bit. I don't know. That's, so again, the problem is, again, you must have the black hole entropy. Otherwise, again, the structure you're building at the horizon is a toy model at most. You must have, and you must take into account this physics. So now we have all these microstate geometries or fuzzball geometries, which are basically a top-down construction in string theory, which has all the three properties. And this is the largest family of solutions known to mankind. Just to advertise, this is the Einstein since they have been found. I don't think anybody has found a bigger family of solutions. Essentially, they involve functions of arbitrary function of three variables. So that's a function of one variable. That's an infinite number of Fourier modes. Function of three variables. That's triple infinite number of Fourier modes. And again, people who do GR, they're cohomogeneity 5. So yes.
You're assuming that the microstates have a geometric description in for now.
I'm trying to do as much as possible.
Because in principle they can, in string theory.
I'm just trying to go as much as I can with geometry, see what lessons I can learn, and then we can go from there. But for now, and the point is, if you compute the entropy of these guys, you don't get the black hole entropy, but you actually get an entropy which is much bigger than the entropy of matter. So if you just look at random stuff in the universe, I don't know, dust or something, the entropy of these guys is actually much bigger, parametrically bigger than the entropy of normal matter. It's just that we don't have the black hole entropy yet. And the point is, in this superstratum thing, it was very important. We called them superstrata, and we had the paper called Habemus Superstratum. We were very happy. It's very important that we were struggling for many years. And it was only after Rodolfo and Stefano and David Turton did some string emission calculations that actually we learned how to do them properly, and incorporated some extra fields which we didn't have before in the ansatz, and then we were able to do them. If we didn't have the string theory input, we were just going blindly around. So it's very important that you understand that you have string theory telling you that these fields must be there, and then you go in supergravity and you find that if you put these fields, everything becomes nice and you can find a smooth solution. If you don't, so it's really like it's a very nice interplay between string calculations, string emission calculations from the D1D5 system, and the full blasted supergravity solution which enters into this game. So the question is, okay, great. Why are these geometries not collapsing? Okay, I told you that they stay at the horizon. Why do they stay at the horizon? The reason is that they have some magnetic fluxes and some cycles. And when you have a cycle which has some flux on it, what's happening is that if you want to squeeze the flux, if you want to squeeze the cycle, the energy of the flux becomes bigger. So fluxes with cycles are actually the only reason, the only way to keep something from collapsing. If you build something horizon-sized and you want gravity squishing you in, the only way to avoid collapse is to put some flux on a cycle, and this flux makes the cycle incompressible. And this was shown by Gibbons and Warner that this is the only mechanism to avoid collapse. So anybody can say, great, I have a mechanism to give structure the horizon using some quantum, some handling, I mean, my loopy thing, I don't know, I have some quantum thing, and I put something at the horizon which is quantum. Great, there's a Hilbert space, you'll have e to the s possible microstates. If any solution which in the e to the s dimensional Hilbert space has a class symmetry, it must be a microstate geometry. Microstate geometries are not something which are like optional. It's essentially, if you build something and you say, I have some structure at the horizon, great. This structure will have some semi-classical limit. Somewhere there'll be
sorry, but what about orbifold?
orbifolds are actually in this, orbifolds are actually in this thing.
Well, the geometry is collapsed, but the string is not. There is the string sees a BMU field, but the geometry from is collapsed. Is singular.
No, it's important. So the B field on orbifold is actually a gauge field. I'm talking about putting a field strength. So if you have an orbifold, for example, if you have, for example, an orbifold, I'm not talking about putting a B field on the 2 cycle. I'm putting a field strength on the 2 cycle. So I'm putting the H3, for example, on a collapsed 3 cycle. So orbifolds can collapse, but that's because they have a magnetic field, a magnetic potential, which is again, the school physics there. What I'm talking about here is putting a field strength on them. So for example, if I have an orbifold, if you have, for example, some Zeon orbifold, you can put an F2 field strength, the Ramon amount 2 for field strength on the orbifold. And then you see that the orbifold actually pops up and bubbles up, and you cannot compress it. But it's an F2. You need a field strength of a field. If you put a B2, indeed, the orbifold can collapse, and absolutely, you're right. So sorry, I misspoke. It's field strength. It should be magnetic. When I said flux, it should not be flux. It should be field strength. Absolutely. Yes.
But then this rules out the possibility of building microstates for neutral black holes and.
No, it doesn't. Fluxes.
Flux.
Yes.
Means that you have something that is charged. I mean, this object only appear when you have some charge or.
Yes, but you can have charge which is positive and negative, and then angular momentum can also give you charge. So angular momentum, okay.
No, but I'm talking about, say, Schwarzschild black holes that have.
I'll have a slide. I'll come to that in a second. I'll have a slide about that. It's not my work, but I'll have a slide about that. So the point is, again, it's really these fluxes which keeps the stuff from collapsing. There's no other way to keep it from collapsing, and one has to live with the consequences. There's nothing. There's no other way to avoid collapse using in semi-classical physics. There's a 4D perspective. I mean, many of these solutions they become Deneb multi-center solutions, which can have Gibbons-Hawking centers of negative mass, and those Gibbons-Hawking centers of negative mass and negative charge, they basically violate all your GR theorems which tell you that you shouldn't put anything at the horizon size, because again these objects are really negative mass, negative charge D-branes. They're string theory, oriented pods are like that. But in other theories, you cannot control them. So that's basically usual. It's again, but from a 4D perspective, again, this is highly unusual. This is not like your general just have a Lagrangian. Let's put a few more fields and let's play. This is highly unusual. Again, it's very because usual matter just falls in the black hole. So it's really the 4D reason. The 4D understanding is that you really have this weird object which come from flux and topology in higher dimensions. And until last December, we only had the solutions for supersymmetric black holes and for extremal black holes. I mean, we didn't have any solution for non-extremal black holes. So until last December, when I was giving this talk, I was saying yes, but we only have SUSY and extremal black holes, and I had to wiggle my way around to tell you that maybe we can learn something. But then last December there's a paper by Pierre Heinemann, my ex-student, with and then a serious work with him and Ibrahim Abah, where they actually build systematically non-extremal microstates using some new technology. How to build. We've been trying to build them for 17 years, and again everybody has been through Saclay. Oscar, I think when we hired him, I asked him to build these kind of things. I mean, he looked at Klebanov-Strassler and fluxes. I mean, we hired Bogdan to do these things numerically. I mean, we've been trying like crazy for 17 years, and God is my witness. We really tried. I mean, I really tried, and I really spent all my energy to build non-extremal microstates, and I couldn't. And those guys did it. It's a very cool. It's a very cool symbiosis. You have basically some torus. Let's say you take some 6 torus, and you take the space-time. What we're doing going in Saclay all these years, we're keeping the torus frozen. So looking at some 5D supergravity or some 4D supergravity, and trying to build these bubbling solutions, and we couldn't. What Pierre and Ibo did was to actually collapse the torus as well. So they actually collapsed the torus cycles in the geometry, and you can show that as you collapse the cycles, you can still get a smooth solution when the torus cycles collapse. Let's say you have a T6, so this is a T2 times T2 times T2. You can collapse this cycle here, and you can collapse this cycle here. And at this location, for example, you can show that you have a smooth R4. And then here, for example, you collapse this cycle from the torus and this cycle from space-time, and you have a smooth R4. And it's a really amazing piece of geometry. You guys, I mean, I think everybody should read this paper. It's really a masterpiece of constructing solutions and so on, using bolts and using torus collapsing. And they were able to actually build bubbling solutions for non-extremal black holes, honest to goodness bubbling solutions, arbitrary centers, as many centers as you want. So I'm not talking about, 1 solution or 2 or 3. I'm talking about, an arbitrary number of centers. And moreover, they're able to get Schwarzschild microstates. How do they get Schwarzschild microstates? Again, in answer to Massimo's question, you actually put flux on one cycle, which is negative, and then you put flux on the other cycle, which is positive. And what you can do, you can get this positive flux and negative flux, and then you can arrange the bubbles not to, there's an attraction, of course, between them, but you can have this bolt, which is in the base, which gives you a repulsion. So they get some solutions, proof of principle for now, where they didn't have, anti-brane charge here, positive brane charge here, and some bubble between them. Of course, the branes want to attract, but the bubble keeps them separated. There's a discussion whether these things are stable or not. There's a discussion whether they have an ADS-CFT correspondence or not. In the meantime, Bogdan and Anthony Hoop and Nick Warner, and Rodolfo and Stefano also collaborating with them, they found another class of solutions which are again non-supersymmetric, asymptotically ADS though. So they don't have asymptotically flat. Those guys are asymptotically 4D. So if you want to do observation, they are your working horse. But there's another class of superstrata which Bogdan and Anthony and Nick found. And they have a nice CFT interpretation. So if you're more into ADS-CFT things, there's another class of solutions which was found around the same time. So, but for the purpose of 4D physics, this is really the first revolution going on in a long time. So yes. No, they are Einstein-Maxwell solutions. So Einstein-Maxwell solutions, you can embed them in string theory if you want, but in principle you can write them as 4D as 5D Einstein-Maxwell solutions with a bunch of Maxwell fields. So if you embed them, I'm giving the string theory embedding because I'm a nice string theorist, so I have to give you my string theory embedding. But if you just want them at the level of GR, it's just Einstein-Maxwell. You don't even have magnetic terms. Yes. Sorry. No. Maxwell fields also. You need to have some negative charge and some positive charge. So it's really Einstein-Maxwell. It's not. I mean, the overall solution, the overall charge is 0, but you need to have locally the fields.
And they have no rotation, and they are non-rotating.
Absolutely. That's exactly what I have the next. So essentially, that's exactly my next point. So the question is, okay, great, to have all these solutions. What can we do with them? Can we understand? Can we use them to understand? Structure the horizon? In an ideal world, I need to construct typical 4D neutral Kerr microstates. I need to construct some rotating things. These solutions that's the ideal world. Ideal world, I need to build all the microstates of the 4D black hole, Kerr black holes, neutral, and compared to the gravity wave data. In the real world, I have 3 options. Option number 1, which is the poor man's option, use extremal solutions, charge microstates, which are like extremal supersymmetric or maybe almost supersymmetric. Okay, they are charged, they are extremal, they are not the same as the black hole, but you can still get physics out of them, and you can hope to get some universal features, and that's something which we've been doing for all these years. There's another thing which again people in the audience did, and it's something which if you put your formal string theory hat, you shouldn't like it. So, essentially you can take uncharged Kerr black holes and you can compare them to charged microstates. On one hand, you say, okay, you shouldn't do that. It's apples and oranges. If you just put your formal math hat, you shouldn't do that. On the other hand, again, people are starving for physics. And if you want to get physics, rather than using boson stars or Graban stars, it's much better to use a known solution of string theory, obeying equations of motion, and, really giving all these extra features. It gives you much richer physics than, some simplified toy model. So, really, it's an intermediate phenomenological option. And when I saw the paper by Paolo and Massimo collaborators, I was like, oh, come on, those guys are doing apples and oranges. But then I realized that, look, if you think as a phenomenologist, you really have to, stretch things a bit. You cannot just put your formal string theory hat and say that I'm only doing poor stuff. But then now we have this new solutions, this Hyman-Bar non-extremal microstates, and in a sense, we can do more stuff. I mean, we can do more stuff. The problem is, at this point, they're only they only have non-spinning ones, so they're all static solutions. They don't have stationary ones. I mean, they can open magnetic fields. So this is the limitation. I think it's a technical limitation. I think they'll be able to put them at some point, but the stuff which exists at this point is just non-spinning solutions. So those are our 3 options, and we can take them from here. Yes. They don't have to be neutral. No, that's the whole point. You are trying to get them to be. Sorry.
But we try to get neutral solutions because it's a prediction from astrophysics that these objects should be neutral. If your model has naturally a charged case, then we should look for charged black holes. So the neutral requirement comes from astrophysics, but if you're saying that this charge comes from a fundamental mechanism, then we should just look for observationally for charged black holes.
The problem is observation charged black holes don't exist, so we don't have them. So the whole point is to build structure the horizon for the black holes which you can observe. So the black holes which you can observe at this point, okay, I mean, Kerr, and that's the most I can do. Maybe Schwarzschild with some luck, or like Kerr with a very tiny amount of spin. So those are the black holes we have in the universe. That's what I want to get the structure of the horizon for. Now the problem is in string theory, we get the easiest stuff is extremal and charged. That's the easiest. Okay, easiest. I mean, it's still like homogeneity 5 solutions and functions of 3 arbitrary functions of 3 variables. So it's still crazy, but that's something which we can do. And basically they're all charged, and they also have mass equal. They always have mass equals to charge. So they're not neutral; they're also extremal. So for Fino reasons, for phenomenological reasons, you can argue that this is just some crazy black hole in some corner of parameter space, which string theory is discussed, but it's not the real world black hole. Now that you have neutral non-extremal microstates, you can say that okay, non-extremal microstates have more rich physics. They can have some features of the real world black holes, and in principle they can also get Schwarzschild microstates again, which are neutral. So that's the advantage of the new method. Yes.
So, but none of these are typical solutions, are they?
No, at this point we only have. So the point is, at this point I'm trying to construct anything which I can control. Mm-hmm. We have no idea yet of typicality, but we have some solutions which are, and I have a huge number of them. I have more than all the matter in the universe. So I can build more of these solutions than all the baryonic matter in the observable universe. I can build more of this by just using these methods. So I have you can think about them as a new state of matter which has more entropy than anything else in the universe. This is the obvious thing to look for. Now, of course, if tomorrow somebody comes and says, but I have this other solution which involves some gas of fractionated strings or something, and I could bring the solution for entropy, of course, head down. I'm very willing, if people find something with more entropy, I'm very willing to say that we should look for those.
But you don't have exponential of area.
Of course, no, we don't have exponential of area, but we have exponential of the mass to the 5 quarters, which is actually again more than all the baryonic matter in the universe. So anything which you can get from matter fields, scalars, baryons, gravastars, whatever normal matter you put, those guys have more entropy. So what I'm saying is that, of course, we don't have yet the exponent. We don't have yet the exponent of the black hole, but we have more than anybody else, and we are clearly getting the closest to the black hole. Yes.
Relation in this.
Of course. That's what I said on the first slide. They always have the same radius in the black hole.
For these neutral ones.
Oh, for the neutral ones, yes. They have. I mean, the paper appeared in March, so it's basically a brand new paper. The one by Ibu and Ibrahim Abba and Pierre. So they have. So for the Schwarzschild one, they have a mass and radius, and they look at the deepest redshift. They have a funny structure at this point because they only built one. Proof of principle example. So they haven't looked at all the space of all the possible Bob-Bob solutions.
In this, at the beginning, you said that you need a solution for every mass in every radius.
Of course.
So
they have the same growth as the Schwarzschild radius, but I think they have 1.5 Schwarzschild radii. But their solution, as you increase G Newton, grows at the same rate as the Schwarzschild black hole. If that's the question. So they really have. As you make gravity stronger and stronger, they grow. The reason is that they're solitonic. Again, they're solitonic because.
But so they grow not as a Schwarzschild black hole.
They do. No, they do. They do exactly.
You said m to the 5th force.
No. That's the number. That's the entropy. That's the entropy. No, there are two things. One of them is the entropy of the solutions. And if you want to look at, if you want to build e to the s solutions, you can ask, okay, how many can we build right now using supergravity? And the answer is 10 to the e to the mass to the 5 quarters, charge to the 5 quarters, which is, basically that's how many solutions we can build in string theory. Now, that's one question, which is about how many solutions we can build at this point, but this doesn't tell you how many solutions are there, because there could be solutions which are not described by our supergravity methods. I'm a supergravity guy, I can only build so many solutions. I've already built the biggest number of Einstein solutions to the
Okay, and for large mass, you need large charges?
No, so the extremal ones, which are the ones where you can build most of the...
No, I'm asking about the neutrals.
The Neutron ones, they only have like, one or two solutions known at this point. Because, they are very hard to build.
Yes, but what I'm asking is, in these solutions, for larger masses, you need larger charges.
The charges are zero, but I don't know, the total charge is zero, but the clusters, no, I think you can do more clusters. I think you can do, okay, I don't know exactly, so, I don't want to answer. I mean, Pierre is giving a tomorrow seminar in Paris. I mean, he should have been here, but, fortunately he couldn't come. So I think you can build multiple clusters of small charge, positive and negative. So, but, I think they only have at this point 2 clusters. So at this point they have a solution which looks like Schwarzschild, and then at some point it has like, two deep spikes. So, it's not a typical state of any sort. But that does satisfy the growth. It does grow with G Newton the way the Schwarzschild black hole grows. So the ratio between the radius of this thing and the Schwarzschild radius is constant as you change G Newton, which is already like a big achievement. Because again, normally if you build, any random piece of solution, it always becomes smaller as you make gravity stronger and the black hole becomes bigger. Their stuff grows with the Schwarzschild black hole. So that's. So great. This is the first. So now I'm going to go a bit into more detailed into a more detailed discussion. So there's a question. Okay, great. You have all these solutions. Again, you have the extremal ones, you have the neutral ones, and so on. There's a question. Okay, do they have any differences? Any difference between them and the black hole? The big idea is that if you take the curved black hole which has vacuum in the horizon and you spin it, you get some multiple moments. Mass, monopole, quadrupole, dipole, and so on and so forth. If you spin a ball of dust or a ball of liquid or a solid shell, or some other black hole replacement, in general it will have different multiple moments. So if you spin back, you get one structural multiple, but if you spin anything else, you get another structure. And the question is, if you spin this ball of fuzz, I mean the stringy, non-perturbative, big brain, big fat bound states which you are building, the question is, what do you get? Do you get the same results as the black hole, or do you get something else? And ideally, again, we should get microstates of Kerr. We don't have them. This Hyman-Baha just Schwarzschild, we don't have rotation yet, so okay, hopefully something will be coming up. And there's a simpler thing, you can try BPS, almost BPS, running volt, some other solitons. There's a big question, is there any difference between those and the black hole? And in principle, again, people could do gravity waves, it's an important question, because in principle, if you find the difference, which is systematic, all of them have the same difference. Gravity waves from emeries, which will hopefully be measured from LISA, can measure multiples, and you need 3 of them to rule out Kerr, you need 4 of them to rule out the boson star. So if you can measure like 5 or 6 of them, you can really wipe out the whole field. I mean, if all the string theory microstates have some quadrupole and octopole moments of some sort, and you come up with a different number, then you can rule out a lot of solutions. So that's in principle it's something which is experimentally within some sort of reach in hopefully our lifetimes. Now, gravitational multiples, I'm not going to go too much into them because many people in the room know about them, and those who don't, they can. I mean, it's some simple stuff. Again, in electrodynamics, you have like monopoles, dipoles, quadrupoles, octopoles. You just have an expansion of all the fields at infinity. In GR, it's a bit more complicated because you have coordinate transformations. The naive ones are not well defined. In 5D, for example, they're not well defined. The 5D multiples, it's a complete pain. Apparently, you can only discuss. You can only go get a quadrupole. I mean, anything above octopole is better defined in 5D. So in 4D, luckily, we have 2 formalisms, Gerald Hansen and Thorne, which can allow us to read from a solution what the multiples are. And for the Kerr black hole, again, this is a known good old result. For the Kerr black hole, for example, the solution depends on m and the rotation parameter. And the multiples, the even mass multiples are finite. The odd rotation multiples are also finite. The odd angular momentum multiples are finite. But the odd mass and the even angular momentum are 0. That's the feature. If we take the Kerr black hole, this is a known result from ages. And for Kerr-Newman, it's the same. Kerr-Newman is basically the same result as Kerr. So putting the charge doesn't seem to affect the multiples. I have no idea why. But okay, I think Daniel is working on it, and I think he'll still have some upcoming short notes explaining the things, clarifying a bit. But for me, it's all GR mistakes from 30 years ago. So the question is, okay, let's take the 4D black hole, and okay, we have all these zero multiples. The odd mass multiples are 0, even angular momentum multiples are 0. What about their ratio? You can look at the ratio of vanishing multiples. They have 0 over 0. But you can take the Kerr black hole and you can deform it. You can take the Kerr black hole and you can put it in string theory. And you can build a big fat STU black hole. You just take your favorite compactification of string theory. There's a super mega big fat STU black hole which has 4 electric charges, 4 magnetic charges, mass and angular momentum. You can also dualize a bunch of times. You can get 56 charges, and you can do the whole. You can use the full orbit of string theory. So in principle, you can do like, you can deform the Kerr black hole into some super mega big SQ black hole. And the super mega big SQ black hole, what you find is that the multiples depend on 4 parameters. One of them is the mass, angular momentum, the rotation parameter, which is not linked to the angular momentum like for Kerr, but it's a bit different, and some other term which is called D. Those of you who know the Rashid-Larson black hole, this D is non-zero for Rashid-Larson, but it's actually 0 for electric black holes. So in a sense, the D is some sort of pointing vector between electric and magnetic charges, and you can actually compute the momenta of this, the multiples of these black holes, and what you find, and then you can say, okay, great, I have this curve, this 56-dimensional space of solutions, and I can compute the multiples. They're all going to be finite, and then I can take the limit when I go back to Kerr. So in the Kerr black hole, the ratio of multiples is 0 over 0, but I can compute this ratio of multiples for this big fat string theory black hole, and I can obtain the ratio of multiples in Kerr by taking the limit of this big fat SU black hole when it goes back to Kerr, by just putting the charge away, taking the dipole charges away, and I can get a ratio. And for example, for the Kerr black hole, you can compute M2S2 over M3S1. S2 is 0 for Kerr, M3 is 0 for Kerr. So for the Kerr black hole, this is 0 over 0. But if you deform the Kerr black hole into this big fat space of string theory black holes, you find that this number is 1. So that's a new number describing the Kerr black hole. And there are more numbers. For example, you can take ML plus 1, ML plus 2 over those, and you can find some numbers, and they have some ratios. Daniel doesn't like it, but I call them Meyerson numbers because it was Daniel who first found them. I know he doesn't like it, but people should get the credit. So basically, those are new numbers describing the Kerr solution. They're new numbers, and they're universal, meaning that if I embed the black hole in string theory, there's a 56-dimensional space of all possible charges. However you go in the space of charges, you come back to Kerr, you get the same results. That's something which I think is quite puzzling. I mean, if you ask me why, I don't understand. It's just an experimental fact at this point. But the point is, you have these extra parameters, and what they do, the fact that you have these ratio of multiples, what they do is that they constrain the small deviations away from Kerr. So let's say you measure, with Lisa some embryos, and you find some dipole charges and so on, and you find some small deviations away from Kerr. Then you can ask, are the small deviations consistent with the Meyerson numbers or not? And the point is, if the small deviations, so again, you have the Kerr result plus a small deviation, the small deviations must be constrained in a very powerful fashion. What this is saying, what all this work is saying, is that if you look at the deviations of the black hole away from Kerr, they all must be controlled. I mean, their deviation away from Kerr is controlled by one parameter, which is called epsilon. Everything else is determined by the solution. So if you find any deviation away from Kerr, a small deviation away from Kerr, which doesn't satisfy this criteria, then this deviation is actually not compatible with the string theory small deviations, and with the small horizon. So there's something which we found quite puzzling, that all the deviations away from Kerr are constrained by just one parameter.
Yes. So, but this is for this family of solutions connected.
Oh yeah.
So this is only for the family of solutions that you have, which I mean, may not be the most general solutions you can get in a string theory.
56-dimensional SQ black holes. I think the string theory is the most general one. I mean, I don't think string theory at this point.
Right.
The way you put the Kerr black hole in any theory, all the possible charges. If you do these deformations, I think you'll get the same Meyerson numbers when you go back to Kerr. Now, there's a question actually about non-string theories, and that's what I have here. So you can also modify gravity without thinking about string theory. You can just say, okay, let's beyond Hornetsky, and I can build a black hole in my Hornetsky or favorite modified gravity theory. And then you can ask, okay, let's say I have a modified gravity theory with one parameter. I build the new Kerr black hole. I calculate the Meyerson numbers, and then I go back to Kerr. Do I get the same numbers as the string theory ones or not? That's a question actually. But in string theory, all the black holes I have, they all, I mean, again, all the embeddings, all the charging up, because string theory comes for you very naturally. It comes from you with like some magnetic fields, some electric fields, and some interaction between them. So it's all very consistent, and all the deformations away from Kerr, they are again specified by these numbers. If you do some other modification of gravity, they could be different, absolutely.
Actually, yeah, related to your last question, I think the answer is no. There are already theories in which these ratios are computed and they are different between different theories.
Oh, nice. Okay. So as you go to, but when you go to the Kerr limit, do they
In the
have
Kerr limit.
Oh, okay, nice. Okay, but that's something which I didn't know. So,
Sorry, do I understand correctly? You say that you check these numbers also for solutions which are not in this class, in your microstate class.
So STU black holes, I mean, again, if I just put the most, I mean, the biggest, fattest charge, so, I embed the black hole into the biggest, fattest, string theory extension. So the full, 56 charges, 56 dipole charges, the whole duality group. Then I can dualize to the STU, and then from the STU, I can compute all these things. But the point is, all the dependence on all these ugly charges comes through these 4 parameters, which are like, this essentially the symplectic invariant between the magnetic charge and the electric charge. There's an angular momentum parameter. So all this invariance comes through some parameters, which are basically, is it n equals to supersymmetry? So if you embed them into some other theory which is not supersymmetric, maybe it's different.
No. The sigma model for the scalars and the gauge couplings would be different from.
Interesting.
That's obvious. I mean,
interesting. Okay. It's something which, I mean, again,
I'm not saying that this is not very general, but it's not the most general possibility in string theory.
I'm a torus person, so I do everything torus first. So, but I thought, interesting. So you're saying that if you embed them in some n equals 1 theory coming from some Calabi-Yau, but
I mean, the sigma model for the scalars is not simplex, it's not special scalar or quaternionic.
So then I shouldn't have the same. So then I shouldn't have the same.
No, it's enough. N equal to. I agree that this is most general possibility in n equal to supersymmetric.
N equals to supersymmetric. I see. Okay, good point. Okay, I mean, we didn't calculate those things. Daniel.
Never mind.
No, we didn't calculate those things. Okay, but that's a very good question, actually. Okay, if you ask about an n equals 1.
I mean, you want to put some constraints on your ability of studying this, otherwise you shoot in the dark.
Model and I can, I can just build a bloody black hole. I mean, I think it has been built. I can just take the limits. I mean, I mean, Daniel can do this in half an hour. I mean, okay, I guess, before the next semester. So, it's something which we can compute okay, maybe not in half the next seminar, but, it's something which we can do in half a day, so something which we can check. But I didn't realize that, this thing is coming from the symplectic.
It would be great to find a black hole solution in n equal 1 theories that arise from, say, Calabi-Yau fluxes where you stabilize moduli, etc.
You can take some n equals 1 theory. We can probably put them there.
No, but yeah, there are many n equal 1 theories, but typically they have scalars that are massless, moduli, etc.
You just check one. If you check one, it's enough. So we should find one. I mean, hopefully somebody did. We are in Italy. I mean, if nobody here found the theory and the black hole, this is the. Anyway, sorry.
Yeah, so a couple of comments. So related with modified gravity, typically, we were discussing this the other day, but so there are theories with, say, a fundamental coupling constant, and the structure that you are showing there, there arises naturally, because we have just one coupling, and therefore all modifications are like that.
Oh, nice.
This is why I was saying the fact that this ratio is then sort of, universal in the Kerr limit appears naturally in those cases. And the reason why, people were not so excited of that, because somehow it's incorporated in the theory, is that observationally you don't measure ratios, right? You measure the single quantities. And therefore the real question from a phenomenological point of view is how big is that epsilon in your theory, right? Because if it is super tiny, the ratio can still be finite, but then you are not going to measure anything, right? So this is one point. And related with this, at the beginning you were mentioning MRIs, which would be really great to measure these multiple moments. One also has to take into account that constraints on these multiple moments are already in place from current gravitational wave observations. They are not as good as they would be in MRIs, but still, for example, there are already constraints coming from LIGO and Virgo saying that the quadruple moment of a black hole cannot be, say, more different than, 10% of that of a Kerr black hole. So that already puts some constraint. It's not that stringent, but it's already some.
By the time Lisa flies, maybe
it will be much better. Orders are going to be better.
Okay, no, I got it. Can I just say, so I agree, right? But it's interesting, for example, that if we take this, even this kind of structure seriously, then you see that for example, the quadrupole, which is the first thing that you look at, you say it's measured, to within 10%, but you see that it goes as epsilon squared, right? And so if you take this kind of thing seriously, then you might think, but the thing to look at is actually not the quadrupole deviation, but it's more, the things that are proportional. But just a comment, right? Like something like this might tell you, even though you can't really measure the ratio directly, it might tell you that the effect would be larger in S2 than in M2, for example.
Yeah, I mean, I agree with that. I guess that becomes theory dependent and model dependent. There will be cases in which they are of the same order.
The rotation parameter of curve. Rotation parameter of curve, so the one present in the solution. No. In the black hole, I mean, this the M2, for example, there's an M2 curve which goes like. Yes. So the question is, what is A, and whether it's a small factor or not. So no, A is for a curved black hole, which is like rotating at 65%. A is of order M. So that's so those numbers are actually big. I mean, the epsilon is small. The only thing which is small is epsilon here. Yes.
I said, what is epsilon?
So I'm just saying that if you deform the curved black hole into some space of other theories with some parameter epsilon, the charges and the dipole charges and the quadrupole and the octopole and all these multipoles.
In your
in my case, it's basically, I mean, I have a 56-dimensional space of deformations. So anywhere you go in this 56-dimensional space, you just close the absolute value of your length epsilon, that's your epsilon. So I have a 56-dimensional space of deformations. Anywhere, any direction I go, I can just the length of that to be epsilon. So it's the radius of how far away I go in a 56-dimensional space.
So you cannot tell what's the typical value of epsilon? Is that?
I have no idea. People have to measure the bloody things first. People have to tell me if they find anything. If they find anything, so for example, if people come and say, I found an S2. If people in LIGO Virgo come and tell me that I found an S2. If they tell me that they found an S2, which is like, 1% of Kerr, I would say, okay, so 1% of Kerr, S2 is 1% of Kerr, therefore S4 should also be, this. And if they're S2 and S4 like, wildly different, okay, or at least I find a different S4, then I say, yes, we have a problem here. At least small deformations of Kerr don't work. Now, there's another way to get these numbers to be messed up, which is to actually look at actual structure of the horizon. So again, there we did it for the 4D SUSY black hole, and the group in Rome also did it for the same black hole. I'm going to go a bit faster because I think the time-wise things. I mean, okay, we've been discussing a lot, but I just go a bit faster. So there you can just build structure of the horizon for the you can just build structure of the horizon for the black hole. It's a multi-center solution. You get some bubbles, and you get a solution. And the point is, there's a solution. In this solution, there's something called the scaling limit, which is the place where the solution which has structure of the horizon approaches the black hole. So you think about structure of the horizon, and you make it smaller and smaller and smaller, and you get it closer and closer and closer to the black hole. And what we found is that in general, the structure of the horizon has different multipoles, but the deviations of these multipoles from the black hole, which is large, become smaller and smaller as the structure becomes closer and closer to the horizon. And in particular, at the scaling point, the multipoles reproduce the black hole ones. So that seems to be a feature which is, more or less universal. That the cap, as you approach the black hole, at least for these extremal solutions, the results reproduce the black hole results. Now, naively, and you can also do non-extremal, non-supersymmetric, but extremal, they are called almost VPS black holes, and that's what we did with Ibu and my student Ishwan and Daniel. Okay, some horrible calculations. I mean, Ishwan, who is a French called normal guy, he found some horrible polynomials and so on. We found the result, and punchline, same thing. You approach the black hole, the structure gets closer and closer to the black hole, and the results become basically the same as the black hole result. What about the Heinemann-Bass solutions? In principle, those are the best to do, but they haven't been done. And just to cite my good friend Captain Barbosa, get to work. Grad students, and young postdocs. Okay, a bit of work has been done. So there's some Schwarzschild microstates when they computed the dipoles, and basically what they found is the Schwarzschild black hole only has M0. So what they found was that the even mass multipoles are actually finite, but the odd mass multipoles are 0 for this Heinemann solution. So that's already like some nice result. But okay, ideally you should have like more general story. I'm not going to go through love numbers too much.
Sorry, but that's important for observation. So does the previous slide mean that it's not a universal predictions that odd mass multiples should be different than 0?
That's the question. Maybe their solution is a Z2 symmetry. I don't know. I mean, they only have one solution. It's just a proof of concept which appeared in March.
Okay.
In principle, at this point, our group in Saclay, we are basically going full blast and, going to the solutions. And, in principle, you can build multiple centers. You can build off centers. You can put, at this point, they have equal positive and negative charge. What if I put charge +2 here and -1 and -1 here? I'm sure there'll be some odd mass multiples. But again, we have to think.
Yep.
Sorry? They have equatorial symmetry. But equatorial symmetry is not enough to kill the odd. I mean, bubbling solutions on online, they can still have odd mass multiples.
I guess it's because it's
the same as these guys vanish.
Sorry?
It's equivalent. These guys vanishing means you have equatorial.
For the M1s and the...
For M2M1 and S2M.
Oh, but our bubbling solutions don't have, our bubbling solutions...
But our bubbling solutions are not equatorially symmetric.
The always UPS ones are.
They're not equatorial.
What do you mean? Axisymmetric, sorry, what? Okay, what's it? Okay, slow.
Here is not equatorial symmetric, but it's axisymmetric.
Their stuff is axisymmetric. It's not equatorial symmetric. So they have a Z2 symmetry where they equator, indeed. They have a Z2 with some flip of charge. But it's just, right now, but, in general, you can do their stuff. You can put, 15 bubbles with random flux. In principle, there should be no zero. But again, it's really work to be done. We're very excited about this, and so love numbers again. I'm not going to go through them too much because I'm running out of time. So there's a nice paper by Paolo and friends about black hole replacement and computing love numbers and so on and so forth. Essentially, they go like but they differ from the black hole results by the log of this psi parameter, which is essentially telling you how far away the structure is from the black hole. And for the microstate geometries, we're able to construct them. And we have an upcoming paper with Daniel and Pierre Hyman. We got a bit stuck because Pierre was busy constructing these other solutions. And the point is, you find that some of them vanish, like for the black hole, and some of them, they have a funny value. But the lesson is that if you look at the microstate geometries and you compute, okay, you have to compute the scalar love numbers, and you get some results for the numbers in these solutions. The point is, again, when the structure becomes deeper and deeper, when the throat becomes longer and longer, you approach the black hole results. It's logarithmic the way Paolo found in other theories. So, it's basically, we confirm that, things are happening the way they should be happening. But unfortunately, it's still the same result. So then the punchline is that, okay, they are different from the black holes. So again, coming back to Nayesh's question, if you come back to Nayesh's question, if you want to look at this epsilon parameter, let's say you find some epsilon parameter, which is like, reasonable, but then things don't fit into this like, Kerr perturbations. It means that you have something crazier at the black hole. You don't have a small perturbation on Kerr. So if you find, for example, S2, S4, and S6, not to be given by these Kerr ratios, but to be given by some other crazy things, then you say maybe there's something more crazy. And in particular, this is what, so this structure of the horizon has these more crazy things. So this is a way to distinguish between something funny at the horizon and a small perturbation which keeps the horizon steady. Yes?
Was asking why, before you were saying this is unfortunate, why?
I want to have something bigger at the horizon. I don't know. I want to get observations.
But isn't actually I would say isn't a consistency test that in the black hole limit you get the black hole result?
No. That's the whole point. I don't think so, because again, if I'm spinning a ball of dust, we have a new matter here. Some really horrible string theory stuff made of brilliant physics and cyclones and bubbles and stuff like that. When I'm spinning this garbage, when I spin this garbage, why doesn't it spin like water? Why doesn't it spin like a ball of dust?
No, but in fact, what you're showing here is that if you take a ball of dust and you squeeze it to the horizon side, only in that limit it will spin like air. We will have us.
But some other objects which are, normally you cannot spin a ball of dust below the Buchdahl radius. So that's my point. But the problem is, essentially, you have the structure which you can spin to the black hole, to the horizon size. Maybe it spins differently. I don't know. I'm really confused about this. I know, maybe we should keep it in the discussion. It's one of the things. So on one hand, again, your argument is clear. The geometry looks the same as the black hole geometry in the scaling limit. So no, why don't you get the same as the black hole result? So this is Paolo's. This is your point. On the other hand, in principle, I could have expected different multiples and different known numbers because it's a different dynamics. I have a big fat mass of stringy stuff. Why should it give me the same results as flat space? I'm just puzzled by that. And maybe there are some ways out. Maybe extremal microstates don't have the same, I mean, they have the same multiples as the black hole, maybe non-extremal do, I don't know. I'm really confused why this is happening. Or maybe, as Paolo is saying, spinning structure of the horizon always gives the same result as the black hole in the black hole limit. Maybe, I don't know. I'm confused about that, and it's something which is important to do. I'm not going to go through this. Okay, there are some other things where you can measure when you have this huge amount of states. There's some sort of viscosity, which some dissipative effects come in because you have a huge entropy in this soup. There's a question, okay, can you do any calculation? It's much harder. But again, the problem with this big soup of states, again, you have this big fastball, which has a lot of entropy, has a huge amount of degrees of freedom. These degrees of freedom, they basically eat up everything. Anything which you put there, it gets absorbed by these degrees of freedom. So again, there's a question: if you replace the black hole by this ball of structure, it's possible that you'll get the same result as a perfectly absorbing boundary condition of the black hole. So this is devil's advocate. And when people get reflection, again, and put echoes. I mean, Iosif has really been a pioneer in this understanding. People can try to model reflections and so on. If you take one particular microstate geometry, there's a beautiful spectrum, there's a gap spectrum, you throw a wave in, it goes out, nice reflection. But the problem is there's a huge number of excitations which move this geometry into nearby guys because you have it to the states. So when you hit one of those guys, it basically wants to go in the phase space and it wants to explore everything nearby and information gets lost. Moreover, there's a new phenomenon which was found by Emil and Nick, and then Nates and Sean Hampton and Ishmael Lee, they had a nice follow-up paper which is called tidal scrambling. When you have a string falling into this mess, there are some tidal effects. And these tidal effects can disrupt the string and can create string production and can again have absorptive effects. So there's some new effects here. And there's something which is really important to understand. How does this big entropy and this big phase space affect everything? Do you get really perfect absorption? Or maybe not. There's an argument by Samir Matur that maybe when you have a supertube that the supertube is more rigid and maybe it thinks back. So Samir, for example, he actually believes that some of those things might have a reflection. But it's really something which, I mean, as string theorists, you need to understand. This is something which is just string theory physics, but it's something to be understood. There are some other things about microstate mountains. When you have these microstate geometries, they have bumps. When you have two black holes going around each other, the gravity wave signals, these mountains, there could be some bumps, like on Neutron Stars, for example, you can have mountains. So, you could also have them on these fastballs. I have no idea whether they're typical or not, by how much. Maybe they're all going to be Planck size. I have no idea. Those are the things. And then again, there's a question of what's happening with the averaging. And again, this comes back to the question, okay, let's say I measure my multiples. All my fastballs have some multiples, but maybe some fastballs have positive multiples, some have negative multiples. You have a big mess of things going into each other. So I have no idea. I have no idea when you look at a typical state, what will happen. At this point, you have some atypical states, and that's all we can do. Anyway, so my conclusions is that, okay, you can build self-reporting structure at the horizon with topologies and fluxes. Again, it has, it checks all the boxes, has all the right growth with G Newton, grows like the black hole horizon, quarks like the black hole horizon, and so on and so forth. This is the only kosher construction of echoes. Again, I'm very adamant about that. I know some people like other methods, but this is the only kosher one which has all the physics we expect. I mean, other things are toy models, but they're not constructions. They are toy models. This is a construction. It's a different. I think we're on a different level. And again, until a few months ago, we only had SUSY and extremal non-SUSY. Now, finally, we have anything non-extremal and analytic. For the first time, I'm really excited about those. The ratio of vanishing multiples. Again, there are some windows into black hole. There are some arguments about small deformations. And again, tidal of numbers and multiples, they are different from the black hole, but they approach the black hole values at this point. And I have no idea whether this is universal or not. And thank you.
Hi, thanks for the talk. So in some of your slides, previously you mentioned that the vanishing of these log numbers may be due to supersymmetry. Is it possible? Did I read correctly? And in that case, could you elaborate a bit more on that?
Indeed. So we only computed them for the BMPV black hole. So this is the BMPV black hole, which is the 5D asymptotically flat rotating black hole. So for the BMPV black hole, basically, you can compute them, and they vanish for the BMPV black hole in 4+1, much like for the Schwarzschild black hole. But when the black hole starts rotating, and when you go away from BMPV, when the two angular momentum are different, the structure of the solution changes a bit. So the BMPV black hole, if you look at the way the solution looks, the two angular momentum are equal, and there's a nice SU2 structure which may be responsible for killing them. When the angular momentum are different, then you can get a more richer structure. So, and then it's like for the Kerr black hole, people are still arguing, I think, for the Kerr black hole whether the love numbers are all 0 or not. I mean, I think there's still some arguments. I don't know. Experts have different opinions. Maybe that's there's a spectrum of opinions.
So are you saying that the love number vanish in 5 dimensions?
Yes, the love numbers for the BMPV black hole in 5 dimensions, they vanish.
Because typically in 4 dimensions the love number vanish, but in 5 dimensions is not the. They don't vanish typically. Okay. Yeah, no, it's surprising. It's surprising.
Which kind of love numbers, by the way?
They don't vanish in 5.
They are scalar love numbers. At this point, I mean, again, we only do scalar numbers. So we're just putting a scalar perturbation and we are looking at them. I mean, again, they're not, I mean, normally you want to do gravity love numbers and so on. We don't have yet the technology to do them.
Yeah, so sorry, just to clarify, I mean, I need to. So you are computing the static response of scalar fields on BMPV black holes,
yes.
And you are getting that the scalar response is 0.
Yes.
And like the idea is that this motivates or suggests that supersymmetry may be protected.
I think that maybe, because we're also computing it for the microstate geometries, and basically, so if you use a charge scalar, for example, if you have a scalar and you give it some extra charge, then you get some numbers. So,
okay.
It could be that, massless scalars on these things, they have vanishing of numbers, charge scalars. So, I mean, to do the gravity of numbers, it's a much more complicated game. And, for microstate geometry, which depends on 2 variables, the gravity of numbers are a complete pain. So, it's not, we don't know. But for the ones we know, again, for the microstate geometries, you get some result. And again, for the uncharged scalars, and we get to the, I mean, these results, okay, there's some parameter. These results go to the BMPV result. They vanish as the black hole approaches the BMPV. So this is, so my point is I'm just trying to compute, one tiny example of again, scalar love numbers. And I am getting the same result as the black hole. So.
Thanks. So one last question.
Sorry, okay. So you convinced me about the statics, let's say, of the system, which makes you clever because you can reproduce all the nice features of black holes. But I'm not convinced about the dynamics. So let's start from 2 neutron stars. I have a neutron star binary. They merge, so they are very close. So the single stars are not at the black hole limit. They merge and they form a mass which is just above the black hole limit. It's standard model matter. It starts to collapse, and you're telling me that standard model matter, which is just on the verge of the black hole limit, at a certain point magically becomes this string theory soup made of mass. But what happens that makes this standard, very normal stuff at a certain, there is a magical instant when it just turns into this mess. How does it happen? What happens there?
Absolutely. Yeah. So the point is, no, sorry. Here. Absolutely. So the point is, when you have, I mean, again, you can ask a question even easier. Let's take a ball of dust, which is, again, the mass of the TON quasar. So, I'm talking the biggest, fattest ball of dust. The curvature when this ball of dust gets Schwarzschild radius is going to be like smaller than the curvature in this room. Why do quantum effects appear? Why does this ball of dust transform into this fuzz matter? Because it should, and it should do it here. Again, it shouldn't do it here. I don't care what happens here. When this ball of dust has, like, it's like, galaxy size, and forms this TON black hole, I mean, it should collapse, it should transform into a fuzzball then. And the answer is, again, the only answer which can exist is that, again, you can go backwards in time, but I don't want to do that, is tunneling. So when your configuration has a large enough mass and has a small enough size, it has an entropy. And we know that black holes have an entropy, and we know that the entropy comes from these things. I mean, okay, I haven't demonstrated that, they come exactly for my kind of microstate geometries, but, there should be some microstate geometry to do it. And because there are so many of them, you can compute the tunneling from, the neutron star matter, standard model neutron star matter, into this kind of, possible stuff. And the answer is, the tunneling is of order e to the minus s. This was estimated by Krauss and Matur, and for some bubbling geometries, we really computed the whole this thing with all the factors of 2 in front. So we really have, you can really do the calculation in some particular microstate geometries. You can see that normal they really become these non-perturbative bubbles and the tunneling, but there's a tunneling probability to go into that, and the tunneling is really over e to the minus s. So because you have e to the s microstate geometry, because you have e to the s states available when you have black hole size, then you tunnel. So quantum effects do become larger at that point, absolutely. And that's another question actually in terms of dynamics, what's happening, because okay, we have this understanding of neutron stars, merging and collapsing and so on, and we do like ring downs and so on. But now I'm telling you there's another phenomenon in the room. The phenomenon is like this quantum tunneling. And I have no idea, how to take it into account, I have no idea how to model it. It will not be some, gravity with some extra fields, ring down and so on. I think it will be more complicated. So, that's something actually to think about. And then there's something actually which people need to think about. When you have this kind of tunneling, how does it happen? How does the ring down happen? Is the ring down, classical ring down, or maybe it's different? At some point, people are going to measure gravity wave signals of the ring down much better than we have right now. Maybe there's a signal in the ring down. Maybe this ball of mass doesn't have the same ring down as normal stuff. I don't know. But this is something to look at. But you have this extra quantum effect, which again, nobody has looked at that until now.
Okay, so let's thank Iosif again. And we resume 11.